Alright, so in this video we're going to be covering the third law of thermodynamics. And just like the second law, the third law also deals with the concept of entropy, and what it says is that the entropy of a perfect crystal at absolute 0 Kelvin is exactly equal to 0. And I did go over what entropy was in my second law video, but I'm going to give you a quick refresher of what entropy is in this one. So let me go ahead and get rid of this. Alright, and let me get out my graphic here. Alright, perfect. Okay, this is a picture of the three different states of matter. So we have solids here, liquids here, and a gas here. And let's say here we're dealing with water, so this would be ice, this would be liquid water, and this would be steam. Okay, and I think we're all pretty familiar with this. Here in the gaseous phase, we have the molecules very spread out. They're moving very rapidly. And if you were to cool the steam down, and let's say you turn it into liquid water, then the molecules would still be moving around. They wouldn't be as compact as it would be with a solid, but they're still moving around less than in the gaseous phase. And if you were to cool down the liquid, you would get the same thing happening. These molecules would slow down even more. They would compact together even more. And keep in mind that even in the solid phase, these molecules are still moving around. They're still vibrating. All these molecules are vibrating. These are vibrating a little bit more than the solid, and the gases are vibrating a little bit more than the liquid, but all these are vibrating. Now, what the third law is saying is that in your solid, if you were to remove all the heat from the solid, if you got it down to 0 Kelvin, then what would happen to the entropy? Remember, entropy deals with disorder, right? So the exact definition of entropy is the amount of possible microstates. So here in the solid, the entropy would be lower than the liquid because these are vibrating less than the liquid. So there are less possible scenarios for the solid to be in than the liquid. Therefore, the entropy is higher with the liquid. That's why when you add energy, when you add heat, entropy always increases. And the opposite is true. When you take away energy, when you take away heat, you're removing possible microstates, and therefore the entropy goes down. Okay. Now, why does putting a substance at absolute 0 Kelvin, why does that mean that that substance must now have absolute 0 entropy? Now, if we think about it for a second, remember, if we're going to take something down to 0 Kelvin, then we have to remove heat from that substance, right? We have to find a way to extract heat from that substance. And heat is just energy. It has units of kilojoules, which is the units of energy. So we have to extract all energy away from that substance. And remember, these molecules are vibrating because they have energy, right? And if I lower the temperature, I'm taking away energy. The system has less energy to move around, and that's why the vibrations go down. If I remove all the energy, if I put the substance in a state of absolute minimal energy, then that substance can't move. It can't do anything besides just being a perfect crystalline structure. And remember, the definition of entropy is asking, what is the amount of possible microstates? For a substance that's at 0 Kelvin, it only has one possible microstate, whatever state it's in. The substance doesn't have any energy to do anything else. And that's why we can say that a substance at absolute 0 Kelvin must have 0 entropy. Alright, now I just have to cover one last thing because it's very important when talking about the third law. So let me go ahead and get rid of this. Now, I just spent all this time explaining to you what happens at absolute 0 Kelvin, which is that we have 0 entropy in the substance. And remember, entropy is a bad thing, right? Entropy is disorder. We want to eliminate entropy. So if we can get something down to absolute 0 Kelvin, that would be a great thing. But there's something very important to remember with the third law, and that is that it is impossible to get down to absolute 0 Kelvin. Now, the way I like to think about this problem is kind of how I think of the speed of light problem. So the speed of light is 299,792,458 meters per second. So pretty much 300 million meters per second. Okay, so if you were to ask the question, can we build a spaceship that travels at the speed of light? Right now, we think the answer is no, and I'll tell you why we think that. So something very interesting happens when you accelerate. What happens is that your mass actually increases. So let me just give you an example, and I'm going to make all these numbers up. So let's say you're at 0 meters per second, and you're going to go to 100 meters per second. So I'm just going to make these numbers up. So let's say you weigh 10 kilograms, and you're going to go from 0 to 100 meters per second. So you're going to accelerate. When you accelerate, your mass is going to go up. So let's say it went up by a kilogram. Let's say it goes up to 11. So now you're 100 meters per second, and let's say you want to go from 100 to 200 meters per second. Okay, so remember, you're going the same difference, right? You're going from 0 to 100, now you're going from 100 to 200. It seems like 100 meters per second difference. So it should be the same thing, but it's not. Because in the second scenario, you actually weigh more than you did in the first scenario. So it's going to require more energy to get from 100 to 200 than it did from 0 to 100. And this is the problem with the speed of light. As you accelerate, your mass increases exponentially. So to reach this limit, it would require an infinite amount of energy, which is impossible to do. And that's why we think it's impossible to reach the speed of light. This is kind of how I think of the problem of 0 Kelvin. Because in this scenario, it's kind of like the universe is fighting you, right? So it's almost like the universe doesn't want you to get there. And this is what I think is happening with trying to get down to 0 Kelvin. So let's say you were able to get it down to 50 Kelvin. That's pretty cold. Now let's say that our room is hotter than our substance. Let's say it's at room temperature, so let's say 300 Kelvin. That sounds about right. Okay, now remember, we want to get this substance cold. We want to get it as cold as we possibly can. We want to get it down to 0 Kelvin. But there's a problem. The universe doesn't want heat to go in this direction. The second law says that heat travels from hot to cold. It wants it to go in this direction. And this is the same problem that I was mentioning over here. The universe is fighting you. The universe doesn't want things to go the way you want it to go. So to get it down to 40, it would require even more energy. And to 30, even more energy. Like the universe is fighting you the entire time. And to get it down to 0 Kelvin, it would actually require an infinite amount of energy. And that's why it's impossible to get down to 0 Kelvin. Okay. Yeah, but that's all I wanted to cover for this video, guys, and I will see you on the next one.